Welcome everyone to the annual Bekenstein Memorial Lecture. I won't say too many words today. I'm just going to say that I'm happy to see so many people here come to remember our colleague who has been not only an amazing scientist, but also an amazing human being. One of the nicer people that I have met in time. Today we have a guest who has known the family for many years ago, and she has known Jacob from 1972, and she will say several words. After that, we'll have Barak Kol say a few more words on Jacob and introduce our distinguished speaker for today. So, Chris DeWitt.
Thank you. Shalom. It is a deep honor to be able to address this audience and Jacob Bekenstein's family in particular. My late parents, Bryce and Cecile DeWitt, had long ties to the Israeli physics community, beginning possibly from the days when my mother shared an office at the Institute for Advanced Study in Princeton with Maria Kaufman in 1949, which was followed by the attendance of Professor Rychkov at my mother's school in Les Houches in the first or second year after it opened in 1951. I believe it was at Les Houches in the summer of 1972 when my parents first met Jacob at a session which included Stephen Hawking, Brandon Carter, and James Bardeen. From what I have read online, there was an idea that Jacob suggested concerning black holes, which Hawking disliked, and so he and Brandon Carter and Bardeen confronted Jacob at Les Houches, and ultimately Hawking realized that Jacob was indeed correct. It is written that in Jacob, Hawking had met his match. As the rebel among my siblings, I grew up avoiding anything to do with physicists. But on the eve of my first trip to Israel in December 1982, in search of my Jewish identity stemming from a family discovery, I was glad to have the contact information for some of my parents' Israeli colleagues and friends, including Yuval Ne'eman and Tzvi Pihan, both of whom had been at the University of Texas with my parents. And the reason I wanted to address you is because I remember in particular what my father said about Jacob and the way he said it. He said, "You must look up a really nice fellow named Jacob Bekenstein." And then he added, "He's so nice and such a good physicist and extremely modest." My father disliked the notion of pompous self-promotion, both for himself and by others, and felt that if a physicist did good work, it would stand on its own. And it was obvious by his tone that he had great regard for Jacob, not only as a physicist, but also for his modesty. I did call on Jacob when I got to Israel, and he immediately invited me to come and spend a lovely Shabbat with him and Bila, and I believe 2 of their kids, and 1 on the way. And I knew once I moved to Israel that I could call on him for anything I ever needed. Lastly, I will just add that my dad and Jacob were both recipients of the Einstein Prize awarded by the American Physical Society. And I know that for my father, the honor of being in Jacob's company would have meant far more to him than the prize itself. Thank you.
Shalom. It's wonderful to see all of you over here, the Bekenstein family, students, faculty, everybody. I would like to tell you a few things about Jacob Bekenstein first. So, Jacob was born in 1947 in Mexico City. He discovered, the family later moved to the United States, and in 1972, while being a graduate student in the University of Princeton, he discovered his big discovery of black hole entropy in 1972 under the supervision of Wheeler. According to this, a black hole has entropy which is proportional to its area measured in natural units, in so-called Planck units. And this became the basis for black hole thermodynamics and all attempts to understand quantum gravity. He was recognized by numerous prizes, including the 2005 Israel Prize, the 2012 Wolf Prize, and the 2015 Einstein Prize of the American Physical Society, as Ms. Chris DeWitt just mentioned. He was a professor here at the Raka Institute from 1990 till he passed away in August 2015. Just in a few words, I think to me he was a model scientist. Through his keen intellect and deep thought, he saw further than his contemporaries. We heard an example about the argument with Hawking, or the dispute, or the exchange. And he always kept the focus on physics, especially fundamental physics, always developed his ideas independently and originally. And this was coupled with a unique personality, as was mentioned already, scientific and personal integrity, together with very strong dedication and commitment to the science. Since our previous lecture, Stephen Hawking, the celebrated scientist, has passed away. So it's good to know that despite some initial criticisms and exchange, their names will be forever bound through the Bekenstein-Hawking entropy. I would like to conclude with a part on Jacob by describing the rewards of the scientific efforts in his own words. So this is taken out of his scientific autobiography of Gravity, Black Holes, and Information. He did his master's at the Polytechnic Institute of Brooklyn. And there he computed corrections to the Stark effect. This is an effect in atomic physics where atomic levels split due to, as you know, due to electric field. And then he writes as follows. I was able to work out up to the 4th term of the Stark effect formula. This was beyond what others could get. I got a lot out of the effort, both in mathematical prowess and in physical intuition. I think I worked very hard, but I recall those times as full of satisfaction. My head was always full of ideas on how to extend the results on new situations. It is hard to convey the elation one feels upon perceiving a new idea, particularly one which is sufficiently elaborate that it would not occur to most people. You just have to experience it. Okay? So this is out of his scientific autobiography. Now, before going on to introducing our distinguished speaker, a few thanks are in place. First, I would like to thank Eti Adiel and Adi Mizrahi for organizing this event, especially Eti, who has been organizing it for many years now and with such care and warmth. I would like to thank Eliezer Rabinovich for inviting our speaker to Jerusalem, and I would like to thank Nadav Katz for his contributions as the head of the Colloquium Committee. So now I go on to introduce our speaker. So Slava Rychkov was born in Samara, Russia. He obtained his PhD from Princeton University in 2002. After postdoctoral positions at the University of Amsterdam and Pisa, he got a position as an assistant professor in Pisa in 2007. Since 2009, he's professor at the University of Pierre and Marie Curie in Paris, and later he was affiliated with CERN, and since 2016 at the École Normale Supérieure, ENS, in Paris. Since 2017, he's a permanent professor of the Institut des Hautes Études Scientifiques. It's the French analog of the Israeli Institute for Advanced Study. Okay, I'm joking. They're both modeled after the Princeton Institute. In his work, since 2008, he published numerous high-impact works on the conformal bootstrap, which is the subject of his talk today. So bootstrapping, you know, is this concept that you can pull yourself out of something just by holding to the straps of your own boots. I don't know if you were going to explain this. No. So you remember the Baron Munchausen, who went with his horse into a swamp and pulled himself by his hair out of the swamp. So the idea here similarly is somehow you use some data which appears to be non-sufficient. It looks as if you're without any input, you're getting some output. But of course, this is not the case. Of course, these fabulous results require some input. Only it appears at first as if you're bootstrapping yourself, pulling your boots by the straps. He also worked on electroweak symmetry breaking and the Higgs bosons, among several other topics. In 2014, he was recognized by the New Horizons Prize. That's awarded by the Fundamental Physics Prize Foundation, who's also known as the Theoretical Physics Nobel of the 21st century, some people call it. It's a relatively new but extremely prestigious prize in high energy physics, in theoretical physics, and in other fields of science. And he was awarded the New Horizons Prize by that same foundation. So please join me in a warm welcome of our speaker.
Can you hear me? Okay, well, it's a great pleasure to be here on this occasion, this special occasion, and I'm very honored. So I prepared some thoughts about some ideas that have been relevant. I hope they will live up to this very special occasion. So I've been working since a few years on the conformal bootstrap, which is an approach to the physics of phase transitions. And when you are building something new, you are kind of trying to build it as an antithesis to something which exists. And so in phase transitions, in fact, there are two methods. There is a method of renormalization group, which I'm sure many people are familiar with, and it's mostly associated with the work of Ken Wilson. And there's this other method of conformal bootstrap, which actually, if you look at the dates, it has been proposed at basically around the same time as the renormalization group. But it had a tortuous history, as I'm going to explain. So this is going to be a talk about physics ideas, about history of these ideas, and hopefully about some new ideas of the conformal bootstrap. So I'm a theorist, and but let me start with some real physics, just to make sure that we're all on the same page. There are some young people. So there are many phase transitions, but to catch the ideas that I'm going to present, we just will need the simplest ones. There's really textbook stuff, so you should think about things like liquid-vapor phase transition, where there's water and there's a phase diagram. And it's all extremely well known, but what I want to point out is that on this phase diagram, the phase transitions, which are here marked by the arrows, is the first of the phase transitions because density jumps. But then there's this critical point. And as you approach this critical point, the density difference between liquid and gas phase goes to zero in a continuous fashion. And so as you approach it and you cross this point, we say that it's a continuous phase transition. And the same thing happens in magnets. So you just have to take pressure and replace it by magnetic field. And you take the density difference and you replace it by magnetization. And again, we have the same picture. There are magnetization, positive magnetization, negative magnetization. This is first to the phase transition. And then there's a Curie point, and you approach this point, the magnetization goes to zero, and so you have a second. It's actually an old terminology to call it second order phase transition, but more modern terminology to call it a continuous phase transition. And so these basic experimental facts, they have been established long, long time ago in the 19th century, and the liquid vapor critical point in CO2 was found in 1869. The Curie point was found in 1895. And actually people already in the 19th century, they started understanding why this physics, and they built some phenomenological models, in particular like van der Waals that we studied in the first years at universities. So this is 19th century physics, and the 20th century was all about critical point. So what happens, let's focus on the critical point and try to understand what happens in this facility. Already in the 19th century, people understood that something special happens at this point. And really the stage was set by Landau in 1937 for this drama, who published very influential papers called On the Theory of Phase Transitions. And so what Landau did in this work, in modern language, is that he built effective theory, which has to be valid in the critical point, and he built this effective theory in terms of a field which he introduced a very powerful concept which he called order parameter. And so it's some field which has a multi-component field, 5x, and he understood that the symmetry plays an important role for phase transitions. So when this order parameter becomes non-zero, organization becomes non-zero, the symmetry of the system changes, and so in modern language, that was the first example of spontaneous symmetry breaking that plays such an important role in field theory. But he went further away. He didn't do just symmetry, but he also did some dynamics. So he introduced this concept of Hamiltonian or free energy, written in terms of the order parameter. And so this Hamiltonian, it had, so he proposed to expand it in the powers of the order parameter. So it's an integral of terms which depend on the order parameter. There's a gradient term squared, and then there are various powers. And here I grouped the powers into the even powers, phi squared, phi to the fourth, and odd powers, phi cubed. And the critical point happens when the coefficient of the square term crosses from negative to positive. And so that's if you have a negative coefficient, then the order parameter will tend to become non-zero, and if it's positive, then it will stabilize. But then, for this whole phase transition to happen, Landau realized that there have to be necessary conditions. So, for example, the quartic coefficient has to be positive, otherwise we will not have a continuous phase transition. But also these cubic coefficients, A1 and A3, they have to be zero. Because again, otherwise we won't have this continuous phase transition. And Landau realized that this second condition can happen due to symmetry. So if you read Landau's paper, actually I took the occasion, this colloquially, a nice occasion to read the classics. I read his paper again, and it's a beautiful piece of work. And actually, so for example, for magnets, you have, this is the standard picture, you have a double well potential for below the critical temperature, or a single well potential above critical temperature. And if you have a zero magnetic field and there is a Z2 symmetry, which guarantees that these odd coefficients A1 and A3 are exactly zero. So that's a very simple case. That's a textbook case. But Landau, of course, he did not care about, I mean, actually, if you read his paper, he did not care much about this trivial case. What he was after are the phase transitions in crystals, structural phase transitions, where the symmetry structure is much more complicated. It's governed by crystallographic groups, and it's much richer theory, and in particular the coefficient, the condition that A3 is zero, which for magnets is a trivial condition. In crystallography, it's a very important and non-trivial requirement. And so, because of this dynamics, because of this Landau Hamiltonian, Landau could also understand in his language the fact that the order parameter fluctuates. So if you take the Landau Hamiltonian and you compute the two-point function, correlation function of the order parameter, you find that its decays exponentially at large distances, and the scale of this decay is set by the 1 over square root of this coefficient A2 of t. And so it's supposed to go like 1 over square root of the temperature difference. And so this shows that as you approach the critical point, you get longer and longer fluctuations. And this leads actually to a beautiful physical phenomenon called critical opalescence. And if you haven't seen this in your undergrad physics classes, then you should go to the Wikipedia and look it up. There are beautiful videos. So you take a material, you take CO2, for example, you take carbon dioxide, you drive it to the critical point, and you see that what is a perfectly transparent substance becomes more milky. And so this milkiness is a sign of the presence of this long wave fluctuations of density, in that case, on which visible light scatters and it cannot traverse, and so you have this, it's beautiful. Okay, so this is Landau, great, but this theory is unfortunately not quite correct. So it still remains a very powerful and zeroth approximation to physics, and it's not accidental that we still teach it our students. But it's not the whole story. It's not the whole story as people started realizing relatively recently after Landau's work. And so there are several parts where things go wrong, but one thing that people realized is that Landau predicts very specific values for non-nonenticities at the critical point. For example, he predicts that the heat capacity of the material is supposed to experience a jump, and the heat capacity in the ordered phase is larger than in the disordered phase. But if you do an experiment, for example, with liquid helium, which is supposed to fit, not explained, but supposed to fit in the same framework, you see that it is true that the heat capacity in the ordered phase is larger than in the disordered phase. But it's not a simple jump. You see that there is some interesting singular behavior which is described not by a jump, but by a power law. And so the heat capacity goes as T minus T critical to some power alpha, and so this leads to the introduction of this very important concept of critical exponent. So alpha is a critical exponent, and the holy grail of the theory of phase transitions has become to understand where these critical exponents come from. That's going to appear more and more in the rest of this talk. And another failure which was realized relatively recently is that in 2 dimensions there's an exact solution of the Ising model by Onsager, and it predicts that the heat capacity is supposed to have a logarithmic singularity. So again, in disagreement with Landau theory. And there are other things like that. So you can have similar problems for the magnetization. Again, Landau predicts a certain value for the critical exponent, in this case, beta, which says how magnetization should go to 0. And does not agree with the experiment.
Did Landau predicted a jump in the magnetic phase transition? You are writing similar programs. Yeah. What was his prediction?
For the heat capacity, but his prediction is completely different, completely general. Also for magnetic, it's supposed to be a jump.
Also a jump.
Yeah. But now I'm talking about I'm introducing a different critical exponent beta, which says how the magnetization should go to 0. And again, Landau predicts that it's supposed to be 1/2, but in fact, the experiment, you see that it's more like 4/3, or 1/3, sorry. So these are quantitative failures, but there are also some qualitative failures of Landau theory. For example, Landau, as I said, has a symmetry criterion in terms of the vanishing of this cubic coefficient A3 when the transition has to be second order. But there are transitions. People discover transitions which according to this criterion have to be first order, because there is a cubic invariant phi cube that you can write down consistent with all symmetries. For example, the three-state Potts model of two dimensions, but actually they are known to be continuous phase transitions. So something was wrong, and people realized what is wrong. The reason is that Landau theory does not treat correctly the fluctuations. So the fluctuations are treated either as completely absent. So if you just take the potential, you minimize it, you find its ordered state sources, you completely neglect fluctuations. Or if you try to include the fluctuations via this kinetic term, you assume that the fluctuations are Gaussian. So you completely neglect the quartic term, the fact that you have this quartic term in the potential. You neglect it. And people realize that that's just not correct. So that this is going to fail, and it's going to fail precisely at the critical point. And the reason why it's going to fail is that okay, we have this double well potential, and you have some probability distribution for the system to be either in one state of magnetization positive or magnetization negative. But as you get closer and closer to the critical point, these probability distributions will overlap. And so you cannot assume that they are independent Gaussian distributions. There is going to be some non-trivial interplay. And that was definitely beyond Landau's. And so in the 60s, there were, it was a glorious time for this, when people realized that there was this fluctuation, proven fluctuation. So there were lots of ideas, lots of theoretical activity trying to come to grips with these fluctuations. And I cannot review all this activity, but one story which is very important for my work is this scaling hypothesis, which has been proposed by Kadanoff and by Potashinsky and Pokrovsky in 1966. And so again, I reread the paper of Kadanoff. It's beautiful. It's just textbook. It's written in the way that you read it, and it looks like he understood everything. And so what did he say, Kadanoff and Potashinsky? They said, okay, we don't quite know, yeah, so at the critical point something fishy is going on. There are some fluctuations, we don't know exactly. But what we do know is that at the critical point, the correlation length is infinite. And so this means that the system is going to be self-similar. Scale invariant. But what does this mean in practice? In practice, it means that if you take your system and if you split it into chunks of size L, you have some atoms, but let's just group them in chunks of size L, larger size. Then these chunks, this group system, and that's what Kadanoff writes, is going to react to external fields, which are in this case the magnetic field H and tau, which is the difference of the temperature to the critical temperature, exactly like the original system, provided that you rescale these external fields. So you have to rescale this tau by some power of L, by a positive power of L, and H by a positive power of L. And so this is Kadanoff introduced these two exponents X and Y. And you look at this, well, that's what we know. That's the whole idea of renormalization without renormalization. So why is it without renormalization? Because in this language, Kadanoff did not know what the values of these X and Y parameters are. These were just some phenomenological parameters, which were supposed to be fit from experiments. Because everything, all critical exponents can be easily expressed in terms of X and Y. So what did Kadanoff, what did he miss? Well, what he missed was supplied by Wilson. So Wilson said, and it's an extremely natural continuation of Kadanoff's idea. So Kadanoff said, okay, let me just group system into chunks, and now I just have to rescale the parameters, but I don't know by what I have to rescale. And Wilson said, well, you just compute by what you have to rescale. So, and this is very easy. So he introduced this steps 1 to 3, which we learned which we learn now in grad school, and it seems to us very natural, but apparently it didn't seem natural to Kadanoff, otherwise we've done it. So that's something which we probably all heard of, but I'll be very quick. So Wilson introduced the idea of integrating out, that you take your degrees of freedom, you introduce UV cutoff lambda, which tells you which is the size of your chunks. Then you take the degrees of freedom which have the momentum between lambda and lambda over 2, which means that you pass to larger chunks. But then you compute the interaction of the new chunks, this effective Hamiltonian, which governs the interaction of the new chunks, by taking into account the interaction of these degrees of freedom with the degrees of freedom that you are throwing out. And then you rescale the momenta. K goes to 2k, and you go back to the Hamiltonian, which has momenta in the same range as before. And so when you do this, you are supposed to, if you do everything correctly, you will find that the original Hamiltonian has the same form, roughly the same form as your new Hamiltonian has roughly the same form as the original Hamiltonian, but with rescaled temperature and magnetic field. So which is what was postulated by Kadanoff. And so we have this sequence of RG maps, which H1 goes to H2, goes to H3, of larger and larger chunks. And the critical point is the fixed point of the RG map. So this was the idea of Wilson. And to find Kadanoff X and Y, what we have to do, we have to take this critical point, we have to linearize the Hamiltonian around the critical point, and we look at the eigenvalues of the linearized Hamiltonian. So this gave to Kadanoff's picture the concrete calculational machine which allows you to find, at least in principle, these values of the X and Y and all other exponents. But okay, so you can say that the renormalization group is just a calculational device, and all physics was already understood by Kadanoff. But that's not true. And okay, one surprise which came out from this whole picture is that you say, as we said, X and Y are eigenvalues of the linearized Hamiltonian. But these are just two eigenvalues. What about all their eigenvalues? So you expect that your Hamiltonian, your RG transformation linearized around the fixed point, will have infinitely many eigenvalues. And if you are particularly interested about the first two eigenvalues, it doesn't mean that you should completely neglect all the other eigenvalues. They should have some physical meaning. And so, and this is a very important point in my story, which is going to lead me to the bootstrap. So we expect infinitely many eigenvalues, and it means that at the critical point, there are infinitely many fluctuating quantities. So that's somewhat surprising, because normally if you do physics, you say, well, I mean, I have some physical quantity, and it usually has a very clear meaning, either like magnetic moment or maybe charge, and that quantity fluctuates. That's very clear. But now we are told that actually there are going to be infinitely many other fluctuating quantities with dimensions, scaling dimensions of these quantities, which are going to be a priori not related to the dimension of the original quantity that you started with, for example, magnetization. So in fact, these dimensions delta k, which are defined through this formula for the two-point function. So the two-point function of the quantity ak goes like 1 over distance to the power 2 delta k. So they're going to be the scaling dimension delta k, which can be related to the eigenvalue of this linearized RG map. We are forced to say that the critical state is quite a bit more complicated than what we thought. So not just the magnetization fluctuates, but there is like a ton of other things which fluctuates in unison. And if you want to fully understand the critical state, you have to understand also the fluctuations of this quantity. So that is, if you wish, a very non-trivial lesson which you can learn from this RG picture. But actually, this lesson has not quite been learned. And in most of the studies using renormalization group, you don't care about all these infinitely many quantities. You say, well, they exist, but I don't care. I mean, they have no particular interest. I will just focus on the two leading ones, x and y. I will compute those. But those ones, well, they exist. Okay.
They say that they are irrelevant, right?
Excuse me?
They say that they are irrelevant. It's not just discarded. There's some good argument.
Well, irrelevant is a technical, in a technical sense or in an everyday sense.
No, in a technical sense.
In a technical sense.
Right?
Yes.
That's what people say. I'm not saying.
But they exist, so they exist.
But they say that they don't affect the physics because there's an argument. It's not just that
What I meant is that yeah, they do affect the physics. They affect the physics in subtle ways, which are hard to study experimentally. But if you want to understand theoretically what the critical state is, I'm saying that these fluctuation quantities are an integral part of physics. And that lesson has not been heard for many years. But let me I will come back to this point later on. So, okay, of course, the renormalization group had 50 years of glorious history, and many calculations have been done, and many quantities have been computed which agree with experiment, and there's no doubt that this renormalization group is correct, so it provides correct physics. So indeed, this fixed point exists. But when you start looking carefully, you realize that it exists, but it exists in some platonic sense. What I mean by that is that nobody. Let's take some ferromagnet. Let's take the Ising model. For example, three-dimensional Ising model. It's supposed to be at the critical point described by some fixed point. But what exactly is this fixed point? It lives in some infinite dimensional space of infinitely many couplings, which nobody has seen. You say, well, I mean, there are many things which live in infinite dimensional spaces. But for many things, there exists at least in principle convergent procedure which allows you to recover this object that maybe you don't quite get to it, but at least you have a limiting process which allows you to get it. Not here. So here, so this Hamiltonian lives in an infinite dimensional space, and what you would like to get a fully satisfactory theory, you would like to have, at least in principle, convergent procedure, as we would say, truncation scheme, which would allow you to get at this fixed point, at least in principle, in the limit of infinite computational power. So as far as I know, such procedure has never been found. So people tried to get at it in some intuitive or from various points of view. There were decades of attempts, but basically this has not been successful. And it's not really clear why. So it's we seem to be missing something either on the physics side or on the mathematics side, but this is an open problem to find a procedure. And even mathematicians have thought about it, but so far this has not been possible. So what we do in practice is that we deform the problem so that it acquires some small parameters. So there are several ways to deform it, and the one which works very nicely is the epsilon expansion. So you put the system artificially not in 3 dimensions, but in 4 minus epsilon dimensions. Now, epsilon is a small parameter. You can do computations, and these computations agree with the experiment, so you're happy. You're happy, but you're still left with some uneasy feeling that you are failing Wilson. Wilson said that the fixed point should exist, and we still have not done it. So there is something to be done here. Okay. Okay, so this I'm going to leave the renormalization group for a while. I'm going to go to the conformal bootstrap. So the starting point of the conformal bootstrap, I already mentioned it. So as I said, and this follows from RG, that there are infinitely many fluctuating quantities, and in the conformal bootstrap jargon they're called operators, AK of x, which have, each of them is characterized by dimension delta k, and the purpose of the theory is to find these dimensions delta k. So in the conformal bootstrap, you say, well, I'm not going to find just delta 1 or delta 2 separately. I'm going to try to set up a procedure which will magically find for them all delta k simultaneously. So it sounds very ambitious, huh? And the idea is something like the idea of classifying Lie groups. So the idea is that there is some underlying algebraic structure which makes all of these AKs to talk to each other. And so the reason why they all exist is because they cannot exist without each other. So that's the philosophy, right? But now let me proceed to some equations. So we have to put some equations into this philosophy. And the first kind of physical assumption that we need is that these infinitely many fluctuating quantities are such that any physical quantity can be expanded into them. For example, let's take magnetization. Magnetization is not just the first term, A1. In fact, magnetization is an infinite sum of AKs. So magnetization by itself does not have a well-defined scaling dimension. So to get the magnetization, you have to consider a series which contains infinitely many of these AKs. Of course, if you go to large distances, then only the first term in the sum is going to be important. But it's still kind of important to keep in mind that magnetization is not A1. It's a linear combination. Now, that's a reasonable physical assumption, but a slightly more complicated physical assumption is that, in fact, we should be able to expand into these AKs not just a quantity localized at a point, but also a quantity localized in some finite region. Like anything which happens in a finite region of space, you should be able to expand it into these quantities AK localized at a point. And which point? I mean, you can choose any point on this finite region. In fact, the point can be chosen arbitrarily. And the reason why it can be chosen arbitrarily because the change in the position of x can be compensated by adding derivatives of the fields AK, of the operators AK to this right-hand side. And we assume that the derivatives are also included in this list. So that's a more complicated but still reasonable assumption. And now what we are going to do is that we are going to apply this assumption to a very particular case of the quantity phi of omega, which is just the product of two quantities, A1 and A2. So they could be different numbers here, at two different points. So A1 at x1 and A2 at x2. And so if we believe this assumption, so if these quantities are in some ball, well, they are in some ball. And when I say that they are in a ball, it means that the way I should read this equation is as follows. I consider a certain correlation function where there are this A1, A2, and some other things. And all other things, they live outside this ball. And this equation says that I should be able to replace inside the correlation function A1 and A2 by an infinite sum of AKs with a certain coefficient CK. So if you wish, that's the same equation written as a formula. So there are some coefficients CK which depend on x1, x2, and x. And these coefficients, and it's extremely important assumption, they depend only on A1, A2, and AK. and the theory. They do not depend on anything else that may be happening outside of this sphere. So
why x disappear in the left side equation?
Here,
x1 and x2, but it is also x without indexes on the right side. Yeah,
X. X. So I pick AX1, AX2, I pick X, and then I can find these coefficients. So the coefficients will depend on X. So this idea has been proposed actually by the same people. That's an amazing thing, that the same people who worked in the renormalization group, Kadanoff and Wilson, they also proposed this idea called operator algebra, or as we call it now, operator product expansion and the So it's amazing how these two ideas of Conformal Bootstrap and Renormalization group, they were, at the beginning, they were really together. They were explored by really exactly the same people. So any other questions? So this is a very important equation that makes everything work. So is everyone happy with it? Okay. So, okay, now you see the point. We have an algebra. So if we have an algebra, then we can hope to classify algebras of this type using some algebraification of the algebras. So that's what people thought. And when they proposed this idea, okay, of course, they were looking for ways to simplify their job. So they were looking for some additional symmetries to simplify this task of classification. And they seized on an idea of conformal symmetry. So that's something that I have not yet mentioned. And so before, the only thing which I mentioned up to now was scale hypothesis, scaling hypothesis for scale invariance. So I said that the theory at the critical point is supposed to be scale invariant, so every time you rescale distances, physics does not change. So now I have to talk a little bit about conformal invariance. So in the 70s, when people first introduced this conformal invariance as a potential symmetry for the critical point, they kind of introduced it. Why not? It looked like a nice symmetry to play with. So when Polakov introduced it first in 1970, it was almost like wishful thinking. There was no real argument why this conformal invariance should be there. But now we understand why it should be there. So I would like to say some words why we believe this conformal symmetry is indeed a bonus symmetry of the critical point. It's bonus because you don't have to assume it. If you assume scale invariance, then this conformal invariance kind of comes for free. And the reason why we believe it should be there is related to the existence of a very particular fluctuating quantity which exists in any critical point, which is the stress tensor operator, T mu. So if you take this T mu operator and you couple it to H mu, this is the same as to put your system in a classical gravitational field, so on a classically curved background. Now you would say, well, yeah, what does it really mean if I have a magnetic system and if I put it in a gravitational field? This just doesn't make any sense. Yeah, I mean, in general, it kind of doesn't make much sense, but there are some particular gravitational fields which always make sense, and I'm only going to consider those. And these are gravitational fields H mu, which have this very particular form, del mu xi nu plus del mu xi mu. Because these gravitational fields are actually not fields at all, they just correspond to coordinate changes. So I can always take my system and consider it in different coordinate changes. And that always makes sense, even if you are interested in magnets. And then, so the argument goes as follows. Okay, I'm not going to go through the whole argument, but you know that there is one kind of coordinate changes which are scale transformations, which leave the physics invariant. From this, you conclude that the stress tensor, stress energy tensor, should be traceless. So that's the condition. You conclude that the only way this can happen is if this stress energy tensor is traceless. But then you realize that, okay, if it's traceless, then actually not only scale transformations with the physics invariant, but there are other transformations which with the physics invariant. And these are these conformal transformations, which are given by the formula.
So your relation, similar to that which you have in theory of elasticity.
Yes.
Stress tensor in the formation tensor.
Yes.
Can you derive some conclusion of theory of elasticity? You connect it with gravity, but simulates existing elasticity theory.
Yes.
Can you say about this something?
Well, actually, I mean, you fell on a very particular example, because especially theory of elasticity doesn't fit into this framework, because it's a very particular exceptional theory which has scale invariance without conformal invariance. So here I'm cheating a little bit. So I said that scale invariance always implies conformal invariance, but in fact it's not true. There are some very special examples of theories which are well understood, which evade this conclusion. And theory of elasticity is one of those. It does not have conformal invariance. So you cannot say anything about theory of elasticity using this consideration. You cannot. No. Not conformal invariance. Thanks for asking. But,
sorry, another question?
Yeah.
There are different definitions of the stress tensor that differ by total derivatives, and some of them are traceless and some of them are not. So how do you know which one to use here?
Well, yeah, in some theories, in fact, this ambiguity of stress tensor exists only under very special circumstances. I mean, it exists, for example, in free scalar theory, but it's only because the free scalar theory contains some operators of very special dimensions which make this ambiguity possible. But if you just take a generic interacting theory, then this ambiguity is not going to exist. There's going to be only one stress tensor. Symmetric. Thanks for asking. So, okay, I mean, probably many people have heard about conformal transformations, so I also don't want to be too pedantic here. But the point is that once the dust settles, you discover that in addition to rotations, translations, and dilatations, there exists a new class of transformations, which are called special conformal transformations. They correspond to some vector fields, which are the infinitesimal special conformal transformations, and you're allowed, so you take a correlation function, you move points in the correlation function using this special conformal transformation, correlation function remains invariant. That's what remains once the dust settles. And okay, if you have never thought about special conformal transformations, I'm going to explain to you very easily by this picture what it means. So if you take special conformal transformation does for you this. You take 2 points in your space, fix them, and what it does is that it acts as an expansion near one point and a contraction near the other point. So you're allowed to move correlation functions along the lines of this flow, which starts at one point and ends at another point. So it's a very unusual, like, yeah, you would not guess that correlation functions of the critical theory should be invariant under such a transformation. But they are. But they are. Local field theory tells you that they should be. And so people, so it's this conformal invariance, conformal symmetry, it comes for free. So why not use it? People said, okay, why not use it? And actually, if you use it, then you discover immediately, if you know a little bit group theory, that it's extremely powerful. And it's clear already from the group theory point of view. So if you don't have the special conformal transformations, suppose you just have scale invariance. So you have scale invariance, you have dilatations on one hand, and then you have the usual rotations and translations on the other hand. So they don't speak to each other in any non-trivial way. So as we say in the language of group theory, your algebra of symmetry is not a simple algebra. But if you add special conformal transformations, then your algebra becomes simple algebra. So all simple in the technical sense of group theory. So in fact, the algebra becomes equal to the algebra of the Minkowski group in D plus 2 dimensions. So that's kind of maybe surprising if the first time you see it, but all generators speak to each other in a direct way. And so if you have a simple algebra, so the purpose of symmetry in physics is to give you selection rules. You have some atom and it can only decay in one way and not in the other way. Selection rule. So here in conformal theory, you will have also selection rules, which will tell you that when you have a correlation function of several operators, it's going to vanish unless certain conditions are satisfied. Or if you have two operators and you consider algebra, consider operator product expansion between the two operators, then the third operator will appear with only very particular coefficients. So these are selection rules. And if you have a simple algebra, then it's going to give you tight selection rules. And if you did not have a simple one, then you basically would not get any non-trivial selection rules. Just to give you an example, let's consider the analogy with the theory of angular momentum. So in the theory of angular momentum, you could make this analogy where the third component of the momentum is like rotations, J plus is like translation, and J minus is like the special conformal transformation generator. So everyone knows this quantum mechanical Jz, J plus, J minus. So Jz and J plus, they satisfy among themselves a very simple commutation relation. Jz, J plus commutes to J plus. And then there are commutation relations involving J minus. Imagine that if you drop all these relations, just we keep the algebra which only has Jz and J plus. But it's clear that in this case, you will not have any selection rules. You will, like all your Wigner-Eckert theorem, everything will just go out of the window. So you would be in the same situation if you did not have conformal invariance for critical conformal. So this formal analogy is actually correct. So now, if you use this conformal OPE, if you use operator product expansion in the presence of conformal invariance, then you can say much more. So what can you say more? So this is the operator product expansion as I wrote it before. So A1, A2 is the sum of CK, AK. Now, in the conformal theory, I'm going to take fields AK together with their derivatives, dmu AK, dmu AK, and so on, and I'm going to group them all in something which I'm going to call a conformal multiple. So the leading field in the conformal multiplet, AK, it appears in the operator product expansion A1, A2 with the coefficient CK, which is has dependence on X, which is just fixed by the scaling dimensions of operators delta 1 plus delta 2 minus delta K. And then there is a prefactor, lambda 1 to K, which is not fixed by the symmetry. It's a new parameter of the theory. So I already said that there are parameters of the theory which are deltas, delta 1 to K. Here we have a new parameter, lambda 1 to K. And so now to solve fully the algebra, you have to find deltas, and you also have to find this lambda 1 to Ks. But, and this is the consequence of conformal invariance, you should not bother, I mean, all these other fields, derivatives, now in presence of conformal invariance, they go for the right. So all these operators, they will appear in OPE with known coefficients fixed in terms of because of conformal symmetry. So this is the selection rule I was referring to. So that's the very nice thing of conformal. And so schematically, you can write down conformal theories this OPE as follows. So the product of A1, A2 is the sum of the conformal multiplets times numbers, and all quantities which don't appear in this equation, like coefficient function C, I don't write them because they're fixed by the symmetry. So everything else is fixed by conformal invariance. So actually, I don't know when I started. How much?
Started at 12:15, something like 10 minutes, and leaving some time for questions. Is that okay?
Okay, yeah, should be 10 minutes. So, so I want to make another analogy with quantum mechanics. So you see, you can say that this OBE coefficient being fixed by conformal symmetry, it's something like Clebsch-Gordon coefficients. So Clebsch-Gordon coefficients appear when you take a tensor product of two quantum mechanical spins and you express it as a sum of representations with spins between J1 minus J2 and J1 plus J2. And so there are these Clebsch-Gordon coefficients CJM, which express the products of states as the states in the resulting multiples. So there is a similarity between conformal OBE and Clebsch-Gordon composition, but this similarity is not full. So OBE is not literally a tensor product decomposition, because in group theory conformal invariance would allow any delta to appear in the OBE. So when we write tensor product decomposition, we have to include all spins J between J1 minus J2 and J1 minus J2. So in group theory, we have to include all deltas. But in the physical theory, not all deltas will appear, of course. There's only going to be a subset of deltas which will appear. And OBE coefficients that I introduced, they also have no representation theory analog. So in tensor product decomposition, you just have the sum of representations, and each of them will appear like once or twice, depending on which tensor product. Here we have these real numbers, OBE coefficients, and there are new parameters which are not fixed by group theory. Okay, so now I have to I'm coming to a crucial point. So if you want to use algebra to fix your theory, then the crucial characteristic of this algebra is going to be associativity. So this is called B-associativity. And okay, this sounds very mathematical, but what it really means physically is that I take a 4-point function, A1, A2, A3, A4, of 4 fluctuating quantities, and I compute it in 2 different ways. So I can take first A1, A2, use OBE between them, I get some sum over AKs. I take each one of these AKs, I do the OBE with A3, and then I project on A4. So that's the first way. Alternatively, I can start from 2 and 3, get some sum over ALs, and I do the OBE with A1 and project to A4. So these 2 different ways of computing the 4-point function, they have to give the same result. And that's the condition that we call OBE associativity. Now, since we are at the Raka Institute, I was pleased to recall that for spins in quantum mechanics, an analogous problem was
this is 6J coefficients or 9J coefficients, decoupling coefficients in element.
Yeah, that's exactly what I'm saying here. So this problem was considered by Raka, by the coupling problem. And again, this allows me to stress that there is some similarity and there is some difference. So in case of Raka, this equation for spins, it just has to be satisfied automatically. So it just leads to some automatically satisfied quadratic relations between Clebsch-Gordon coefficients. In our case, this equation is not satisfied automatically. It's only going to be, we have to impose this equation, and it's only going to be satisfied if we fix delta k's, the dimensions, and the OBE coefficients lambda 1 to k's to the correct values corresponding to the given theory. And so, you see, if you look at this equation, the key object which appears is when we just exchange one operator AK in the middle. So this diagram with only one operator AK exchanged, this is something which I call GK of x1, x2, x3, x4. It's something that is called conformal block. And so it's a very important special function of this whole business. it's a known function, quote unquote. So it's some, you can compute it, expanding in some power series, but it does not necessarily have a name, so it's not like a hypergeometric function array. And actually, there was a huge progress in theory of conformal blocks, starting from some work of Dolan and Losberg in 2000, which made this whole renaissance of conformal bootstrap possible. And so now that's it. We have our equation of the conformal bootstrap. We have conformal blocks, GK. We sum them with products of OP coefficients, lambda 1 to k, lambda k 3, 4. So this gives us 4-point function. And we can do it in the opposite order, where we first fuse 2 and 4, and then 1 and 2 and 3. Sorry, there's a misprint here. 2 and 3, and then 1 and 4. And this should agree. So this is the conformal bootstrap equation, and you have to try to solve for deltas and lambdas in this equation. So as I said, this equation was first proposed in the 70s by Ferrara, Gatto, and Grillo, and by Polakov. But at the time, it did not really take off. And the reason being that renormalization groups seemed probably at the time like a much simpler tool to go. So they were realizing that they were up to something formidable. So this was an equation of infinitely many, for infinitely many unknowns, infinitely many equations for infinitely many unknowns. They did not really have any idea how to solve it, so they just dropped it. But then they revived, so this whole story was revived in the 80s for the two-dimensional CFTs in a very famous work by Belavin, Polakov, and Samolotchik in 1984. And so this had an interesting effect. So on the one hand, many two-dimensional theories were solved. Not all, but many two-dimensional theories were solved. But on the other hand, people got even more convinced that this approach can only work in 2 dimensions. Because in 2 dimensions, the conformal algebra is infinite dimensional, while in high dimensions, it's only finite dimensional. So they thought, well, you have to have some help from infinite dimensional symmetry, so this has no chance to work in 3D. And only in 2008 that the whole idea was revived in D larger than 2. And so that's something that I'm hoping to be able to speak now. And so, so there are some reviews and so on, but just to give you one interesting result which came out from this approach, one concrete result, is that it was possible using conformal bootstrap to determine the critical exponents of the 3-dimensional Ising model with many digits. So I'm giving here the numbers, and these numbers are at present the most precise in the world. So they are about 2 orders of magnitude more precise than any other approach. And moreover, these error bars are rigorous. So like in any other approach, you have maybe some, if you do some Monte Carlo simulation, maybe you have some statistical error bars. Or if you do a renormalization group, you will have some also systematic errors because of your summation procedure. But here, we are solving mathematically exact equations. There is nothing, there are no divergences, nothing. So whatever results we get are completely rigorous. And so what I would like to say now is, so I don't have really time to talk about many applications, but I would like to give you the spirit of why is it that we managed to make progress on this problem. So what is it? What is the new idea which allowed us to succeed while the classics they gave up? And so to get the feel, I will consider just the simplest case where I'm going to look at the correlation function, at the 4-point correlation function of 4 equal operators. So I'm going to take A1, A2 equal A3 equal A4. So the external operator is fixed and equal, but the internal operator, the one which was exchanged, AK, can be of course anything. It has to be arbitrary. We have to allow arbitrary. And so if you write correlation function in such a situation, then, okay, this is the equation. It has two terms. The first term is just a trivial term contribution from the unit operator. And then there is a second term, which is the sum over conformal blocks. And in this case, because I'm considering identical operators, the coefficients of this equation are positive. They are squares. So, and then on this correlation function, which is given by this formula, I have to impose the constraint, which is, it has to be symmetric under the interchange of x1 and x3, the crossing symmetry. So these are the two constraints. Now, the reason we made progress is that we started thinking geometrically. So let us do something which at first may look crazy. I would like to look, instead of looking at trying to solve for any particular 4-point function which satisfies this equation, I'm going to look at the set of all 4-point functions which satisfy these equations. So this is the set I denoted S. And this set, which is, we don't know, I mean, presumably, we don't know how large this set is. It may be finite, it may be infinite, it may be unbounded, bounded, and so on. But one thing which we definitely know is that this set is convex. So if you have two 4-point functions, G1 and G2, which satisfy these equations, then if I take the linear combination of these 4-point functions, it will also satisfy these equations. Well, that's kind of obvious because you see, I have this here positive coefficients, so I'm going to be taking linear combinations of positive coefficients. They will still stay positive. And if the correlation function was symmetric, if I take linear combination, it remains symmetric. So that's clear. So this set is convex set. And if you know something about convex geometry, you know that convex sets are tractable sets. Tractable, what does it mean tractable? For example, if you want to, if you are given some general set, which is a given set, and if you're given a point, and you have to ask a question, if you ask a question whether this point belongs to the set or not, if the set is a weakly set, it may be a very, very hard question, especially if this is a set lives in infinite dimensional space, to answer whether this point actually belongs to the set or not. But if your set is a convex set, then these sort of questions are easy to answer. The reason is as follows. If you have a set which is a convex set, and if you have a point which does not belong to your set, then it's equivalent to be able to find a plane which separates the point from the set. So this is the property which is only valid for convex sets, and it makes the whole problem tractable. So, so the set S is a convex set. If you take your operator algebra and if you fix the dimensions of certain operators which appear in the P delta K, then this means that you take a set and you intersect it with some hyperplane. The intersection still remains a convex set. So the problem still remains tractable. So what it means is that you can decide all interesting questions that you can ask algorithmically. And in fact, the way we made progress is that we developed some efficient numerical algorithms based on linear and semi-definite programming, which allowed us to study consistency of low dimension spectra of the CFT. So we have infinitely many operators in the CFT, delta 1, delta 2, delta 3, and so on. We are interested in asking questions about low dimensional operators, delta 1, delta 2, delta 3. And we are not particularly interested in these high dimensional operators, but we know that they are there. If those operators were not there, then the equations that we are solving would never be satisfied. And so we are able to ask questions about low dimensional operators, marginalizing over all these high dimensional operators using these numerical algorithms. So that's the first reason why we made progress. And the second reason is that we realized that it's interesting to focus not just on the set S, but on its boundary. So you have the set, and let's try to push to the boundary, maximizing some quantity. So why is it interesting to look at the boundary? Because, as I said, so when I was proving that that the set was convex, I considered this linear combination G1, G2. This linear combination, it was inside the set, but it did not have a minimal spectrum. Because if a certain operator belonged to both theories G1 and G2, then along this interval containing G1 and G2, then both operators would be present. The spectrum would not be minimal. But if you go to the boundary, then you have a chance to uncover a theory which really has a minimal spectrum. And so we did this. So we started inside the set S, and we tried to go to the boundary by maximizing or minimizing by extremizing various quantities. And then we discovered an interesting thing, that by maximizing or minimizing different quantities, we somehow ended up in exactly the same point, in exactly the same theory. So we found some corner points which corresponded to exactly the same theories. And so at first when we found this, we were very surprised. And we were even more surprised when we found that these points, they did not correspond to just some theory, but they corresponded to the three-dimensional Ising model. So the dimensions that you recover when you go to this point were in agreement with the experimentally known dimensions, experimentally and theoretically known with the error bars, the operator dimensions of the three-dimensional Ising model. So we're very surprised, but then we realized what's going on. What's going on is this picture. The three-dimensional Ising model lies at the very not only does it lie at the boundary of this space of all possible 4-point functions, but it lives at the corner point of the boundary. So it lives at a very special place, at the corner point of the boundary. And if you have something which lives at the corner point, then it's clear that you can push. There is a range of directions in which you can push, and you will always end up at the same corner point. So when we were trying to maximize or minimize different quantities, it corresponded to choosing different directions from which to approach the corner point, but the answer was always the same corner point. And so this was the discovery about the three-dimensional Ising model, which then led to also predictions of the critical exponents, which were very precise. Okay, so I hope that I managed to convey some of the spirit of the numerical bootstrap. So just to say what are its strengths once again. So it allows to put some bounds on the space of possible conformal field theories, numerical bounds, but you postpone the more difficult problem of solving conformal field theory until later, and you settle for something less, which is to put bounds. So these bounds are rigorous constraints, so you can put constraints on the known conformal field theories, on the known critical points using these bounds. But so you did settle for something less, but then you discover as a bonus that unexpectedly some of these bounds that you derive are extremely strong. So there's no reason why they should be saturated by known theories, these bounds, but they are. So that's something that we discovered, that many known theories, like the three-dimensional Ising model, the three-dimensional ON model, the Gross-Leveux fixed points, and many other fixed points that people discuss in statistical physics and condensed matter, they seem to saturate bounds. So why exactly this happens, this is not yet fully understood. So this stimulates theoretical thought. It's called numerical experimentation. So I say numerical, but in fact, this is a bit of an undersell, because it's true that numerical is a big component of this whole program, but it also required some huge analytic progress, in particular in the study of the conformal blocks. And usually this progress happens by also the same people who do numerical analysis. So there's a new community of people which are interested in both analytical and numerical results. It's not usually the case in theoretical physics. But now I have to answer the question in the title of my talk about renormalization group versus conformal bootstrap. And I just would like to say that at present, bootstrap is great, but at present it's not, I would not like to advocate that it's a replacement for renormalization. It's rather like a complementary precision tool. It's a precision tool. Or sometimes it's also a good oracle to answer questions where a renormalization group it gives ambiguous answers. So there are many situations in physics where the phase transition, for example, the order of the phase transition cannot be decided whether it's second order or weakly first order, things like that. And in that case, conformal bootstrap has already played a role in providing a sharp verdict about the order of the phase transition. So there are still many areas in which there is no alternative to RG. And for example, the problem of critical relaxation. So if you take a critical theory, static critical theory, and you have time, and then in general some phenomena with the dynamical critical exponent which is not equal to 1. So I guess you already know the answer to the question. So I think we should be friends, and I think that it's great that we have two complementary methods, and we should have a lot of friendly competition, and I hope that it will lead to even further understanding of the phenomena. Thanks.
Thank you for a wonderful feat of describing the whole theory in one talk and getting to the most recent results and adding so much original insight. I know we're a bit over time, but I'm glad to see there are questions. So please, Nadav.
Maybe it's a bit of a philosophical question, but it's related to things Jacob initiated, so I feel compelled to ask. So, from what I understand, you have an infinite hierarchy of coupled degrees of freedom, which you're solving self-consistently in order to produce an emergent order parameter. But in the end, it sounds a bit, from the philosophical point of view, that you have like turtles standing on turtles all the way down. And the question is, something that Jacob initiated was that there are computational limits to the power of reality to compute these functions and to realize them in physical reality. And to what extent will this play a role in a finite system? What is the computational power? In your theories, it's unlimited, but in reality, it is coarse-grained and finite. And so what is it actually resting upon, this infinite hierarchy of yours? What is the turtle at the bottom?
Well, yeah, it's a deep question, I agree. So Jacob Bekenstein, constraints that he was proposing, they appeared very non-trivially from the interplay between matter and gravity. So here I'm considering a situation which is an idealized situation. There's no gravity here. On the other hand, we think that the physics of the critical point makes sense without gravity. So by decoupling gravity, I'm not modifying significantly the physics of the critical point. So I think that this theories of critical point that we know, be that renormalization group or this more recent conformal bootstrap, they are consistent theories without any need to involve gravity. And they are governed by mathematical laws which are I think within our, I mean, they're complex laws, but I think they're within our ability to understand and within our computational ability to harness. So in particular, these numerical computations that we are doing for the conformal bootstrap, we do not see any exponential increase in the computational power as we compute more and more digits of these exponents. So that's, at least empirically, we don't seem to be running against some exponential wall, as it often happens in quantum mechanics. Here we seem to be okay.
Further questions?
Questions. One, you mentioned that lambda 1 to k is not due to the tensor product. It's not like that's all coefficient.
No.
But you get those in the delta k by solving an equation relating two sides.
Yeah.
Question number one, is that instead of unique solution to the, or the cellular solution to that set? And the second question, I mean, you do have an algebraic structure, which is SO d plus 1, 1. So where does that enter here as far as classification, states, representations? Where does that enter in that formula?
Well, let me start with the first question. So the solution is either unique or there's a finitely many solutions, in which case, if there are finitely many solutions, you have to introduce an independent OBE coefficient multiplying each solution. So this does not lead to the change in the formal structure that presented it, although it complicates the calculation. But in the simplest cases, it's unique. Now, concerning your second question, yeah, algebraic structure, okay, here I was presenting a caricature, but of course it enters everywhere. So there are various ways of presenting the theory. In one way, you could present that I'm dealing, so if I want to be extremely formal, you say that that the operators of the theory are highest weight representations of SOD plus 1, 1, and the OBE coefficients are the intertwining operators between tensor products of various representations and whatnot. So yeah, SOD plus 1, 1. So for example, this conformal multiplet that I wrote, SOD plus 1, 1, it's a unitary representation of SOD plus 1, 1.
One last question, Eitan, did you want to?
Yes, I mean, all that relies on the assumption that you have conformal invariance. I mean, how do you know for a given model whether it has or doesn't have conformal invariance? I mean, in that sense, RG is maybe more general than bootstrap, not just.
Well, it's a long-standing problem to ascertain the precise criteria for conformal invariance. So at the moment, this problem is not fully solved. We understand that, so the current theoretical understanding that generically, scale invariance plus rotation plus translation implies conformal invariance. Now, what does this genericity mean? Usually it's, so this equation that I wrote, T mu equals 0. So I was cheating a bit. So there's a more general equation, T mu equals full divergence of some field, what we call it K, which would be sufficient for conformal invariance, but which would break which would be sufficient for scale, but which would break conformal invariance. But for this equation to be true, this operator K should exist, and it should be a vector operator of dimension exactly d minus 1. And it should not be conserved, because otherwise we are back to this equation. So generically, we think that all vector operators which are not conserved get anomalous dimensions, and so you simply do not have candidates for anything to appear here in the right-hand side. So we believe in this genericity argument, and we are waiting that someone is going to put it on a more firmer ground. For the moment, we are glad that all the predictions from the conformal booststrap that we get using conformal symmetry they agree with our G, but they're just more precise. So it seems like we are not making an outrageously wrong assumption.
Okay, so I know there are additional questions, but Slava will be here today and during the rest of the week. So let's thank him again.